Grade 1 at National Institute of Technology, Trichy. Sir has completed his MTech in Electronics and Communication Engineering from College of Engineering, Trivandrum, and his doctoral work lies in the field of medical image processing from NIT, Trichy. Sir's major specialization includes signal and image processing. His other areas of expertise are IoT in healthcare, augmented reality in healthcare, artificial intelligence, circuits and systems, and hardware for deep learning. Dr. Varun is a professional member in IEEE and a member in IEI. He has his account more than 50 international journals and has presented papers in more than 30 international and national conferences. Sir has also authored the books Basics of Electronic Engineering and Introduction to Electronics Engineering, published by OWL Publishers. He also has 7 book chapters published to his name. Some of his major achievements include Dr. APJ Abdul Kalam Researcher of the Year 2016, awarded by Government of Kerala. He has also received the Canadian Commonwealth Scholarship in the year 2012. Sir is an associate editor in Springer Journal of Physical and Engineering Sciences in Medicine. He has an established network of collaborations both at national and international levels. It gives us immense pleasure to invite you, sir, to deliver your talk on recent trends in biomedical image analysis. Over to you, sir.
Hello?
Yes, sir.
Yeah. There was a connection issue, so I lost some connection in between.
Okay, sir.
Okay, shall I start?
Yes, sir. Yes, sir. Please.
Okay. So today we are going to see the role of medical image computing in and machine learning in healthcare. So as an introduction, so we know that novel imaging modalities are being introduced in medical practices, like starting from X-rays to PET, SPECT, etc. So the availability of well-documented medical imaging, that is known as big data, offers new opportunities for group-wise analysis within specific subject groups. So we know that nowadays there are a lot of data sets available. It's an era of big data. And using this big data, we can go for development of different methodologies for analyzing these medical images. Next is the characterization of normal and abnormal variation between subjects to identify whether the specimen is belonging to a normal or abnormal. Then detection of individual patient anomalies and discovery of early markers of disease onset and progression. Say for the example of Alzheimer's disease. Alzheimer's disease have 2 stages. The initial one is the MCI, that is mild cognitive impairment. And most of the mild cognitive impairment may not be go to Alzheimer's, but sometimes it may go to Alzheimer's. So first, we need to find the onset, that is MCI. Then we have to analyze the patient for a few months of time, and we have to check whether the MCI is progressed as AD, that is the final version. So next is the optimal therapy selection and prediction of therapy outcome. So how to choose a optimal therapy for a particular patient, and we have to predict what is the outcome of that particular predicted therapy. And finally, the correlation of genotype and phenotypes related findings. So these are some of the main points in this medical image computing and machine learning in healthcare. So first we goes to medical image analysis. So as you know, the medical image analysis involves measurements in medical images. That is the extraction of relevant quantitative information from the images. That is, for example, manual measurements by human experts in large 3D medical imaging data sets are not only tedious and time consuming, and it is also impractical in clinical routine. and also subject to significant inter-observable variability that we will discuss in later. So which determines the significance of the clinical findings derived from them. So generally it is easy to analyze a 2D slice of image, right? But we are moving from 2D to 3D, we will get a better view or visualization, but the amount of data involved with the 3D is much higher compared to 2D data. So within this wide variety of medical imaging applications, most of the image analysis problems involve a combination of the following basic tasks like image segmentation, image registration, image visualization, etc. So when we talk about image segmentation, the segmentation involves the detection of objects of interest in that image and defining their boundaries. Okay, so that means we are going to discriminate between image voxels. Voxels means volume pixels that belong to particular object and those that do not belong to the object. That means we are going to separate between the object and its background. So image segmentation is a prerequisite for quantification of geometric properties of the object. So if you want to particularly detect a disease in an organ, so first you need to localize the organ, then we need to segment the organ. So after segmentation, we will get the geometrical details from the organ, like volume, shape, etc. So we can measure from segmented result. So this segmentation can be performed in different ways. The first one is defined by the boundary base. That is, boundary base, we are delineating the contour or surface of the object in two-dimensional or three-dimensional image slices. And second one is region-wise grouping of voxels that are likely belong to the same object. So for example, if you're having a liver lesion, so organ liver you are considering, so that time you are going to do either contour-wise by taking a contour over the entire surface, or in other words, we can go with the region base. That means we have to choose each voxel, that is volume pixel, and the volume pixel which is having the same or similar or nearly similar pixel values can be grouped together to form the structure. So this is the two methods which we are using. And when we come to the image registration, so image registration involves determining spatial relationship between different images. So for example, you are taking an image from a modality, say for example CT at different time instances, and if you want to put it together to form a registered image, you can go for image registration. Or if you want to generate a 3D visualization from a 2D slices, you have to take 360-degree rotation with the 2D slices, and you can register this together to form a 3D image. And in some cases, you want to combine images from one or two modalities. Say for example, generally when you have a nodule in the lungs, the CT image will give you the details regarding the bones, and PET imaging will give you the details regarding the tumor or the nodule. So when you fuse these together using registration algorithms, you will be getting a much more detailed description of the nodule. So image registration can also be used for registering images from two or more modalities. And when we come to visualization, the information that is extracted from the image ideally needs to be presented in the most optimal way to support diagnosis and therapy planning. So when you use some methodology to detect the internal part of the organs, so we need to visualize it properly. Then only the radiologist can identify what are the content inside it and is there any abnormality present. So he need to visualize it properly. So image visualization plays an important role in this medical image analysis. So this will give a correct interpretation by the user of all relevant image data, maximally sophisticated for a specific application. For 3D medical images, the 2D multiplanar visualization is not well suited to assess the structural relationship within and between the objects in 3D, for which true 3D visualization approaches are to be performed. So when you take 2D and trying to generate 3D, it is quite difficult and it is complex. So better you can go for 3D visualization applications so that we can get a 3D view. So that will give you more information regarding the volume of tumor or polyps or nodules formed in a specimen. So when we talk about this medical image analysis, there will be definitely a lot of challenges. So this medical image analysis is complicated by different factors, in particular, the complexity of the data, the complexity of the object of interest, and the complexity of validation. So these are the main three challenges when we face in medical image analysis. So the first one is complexity of data. This means the medical images are typically 3D tomographic images. And the 3D nature of images provide additional information, but also an additional dimension of complexity. So generally we look at the 2D slices, we will get the information, right? But when you look at the 3D information, we will get more idea regarding the organ, but there is more number of data is involved because we are considering 3 dimension here instead of 2 dimension. So instead of processing the data in 2D slice by slice, 3D processing is usually more effective as it allows to take spatial relationship in 3 dimensions into account. So when you consider the result point of view, this will be much better. 3D will be much better compared to 2D. But the problem is we have to process one more slice of information which is in the 3D domain. That is the third domain. Next is the complexity of object of interest. So the object of interest in medical imaging are typically anatomical structures which cannot be easily described by a mathematical model. So the object of interest is mainly the anatomical structure. So we are unable to represent it as in mathematical model. So anatomical structure may exhibit complex shape such as a cortical surface of the brain or cerebral or coronary vessels or bronchial tree in lung. This is having complex shapes. So how we are going to mathematically analyze these complex shapes? That is another problem. Moreover, anatomical structure can show large intra-subjective shape variability due to internal soft tissue deformations. For example, breathing related motion, bowel activity, etc. So when you take the scanning within an MRI or CT, we are breathing and our bowel action is also going on, right? So because of that, these may affect the imaging. So that may create some artifacts in the image. So this is also a problem. And finally, the complexity of validation. So this medical image analysis involves the quantification of internal structures of interest in real-world clinical images that are not readily accessible from the outside. So the assessment of absolute accuracy is often impossible in most applications because of lack of ground truth. So whenever we have to do a classification or a detection algorithm, so we need to get a valid data for training and testing. So if you are not having a ground truth data, it will be a problem because to whom you have to compare your developed addresses. So there is a problem with the lack of ground truth. So this is the complexity of validation. So when we come to the medical image computing, so it develops computational strategies for medical image analysis. And it provides model-based image analysis with appropriate parametric representation. So here we have to develop a model. Okay. So that model should be appropriately parameterized representation of the data. So here the criteria is models need to be sufficiently flexible to account for image appearance variations. So in general, when we use deep learning, so you know that if you are having less number of data, you are going for augmentation, right? So in augmentation, we are rotating, flipping, rescaling, shifting, shearing the images to get more number of images. So in that cases, the appearance of the image is changing, right? Or it varies. So if you define a model, that should be sufficiently flexible to account for the image appearance variations. Even if I am augmenting and giving the data, the model needs to be good in such a way that it can identify the changes in the appearance. So that is the criteria here. Otherwise, if you train using only one set of images and you are giving another orientation image, it may not be identified. So strategies are machine learning strategies such as support vector machine or random decision forest can be used for feature-based classification. So in machine learning kind of application, we first extract the feature by our own, that is handcrafted features. Later we are fixing it or feeding it into the machine learning classifiers. That is one strategy. And second one is deep learning based strategy. So when we compare these two, machine learning is a tedious job because you need to extract the feature from the images after some set of processing. Then you have to feed it into the classifier. And this is good if you have a less number of images in your data set. And if you have more number of data, big data analysis, then you have to go for deep learning because it's tedious to extract a feature from all the images in a big data. And when deep learning is considered, it is an end-to-end learning. So we no need to extract the feature from the image. We can simply give the raw image to the deep learning network. It will learn and it will give you the results. So there is no handcrafting feature selection in case of deep learning. So in the model-based analysis, it represents prior knowledge about the geometric, photometric, and contextual properties of the object of interest in the image. So based on this, we are going for energy minimization. There are two sets of energies in the model. The first one is the internal energy, and it is the measure for its priori likelihood. That is the prior information about the object. And external energy represents the goodness of fit of the model instance to the data. How well the model is fitting to the input data. That is what representing the external energy. So based on these two, we are going to classify. And for the feature vector to be classifier or a regressor, it is depending on our application. So for example, if you are going for a classification kind of application, you have to go for a classifier. And if you are going for a denoising kind of application, you have to go for regression. So the drawback for this model-based image analysis is the initial set of features predefined heuristically are likely suboptimal because it is not optimal, it is just suboptimal. So we are not able to get the expected outcome. So we need to train again and again to get a better representation. So when we consider the computational strategies, we have two main computational strategies. The first one is flexible shape fitting and next one is fixed classification. These are the main two computational strategies we are using in model-based analysis. So we'll see the first one, the flexible shape fitting methodology. So here the figure shows a flexible shape fitting example of a statistical shape model for left lung in a 2D thorax radiography. So here the model is constructed from a set of example shapes that we manually delineated in images of different subjects. So if you see here, you can see different representations of the left lung, right? So this is we are manually drawn, okay, or manually extracted or delineated images of different subjects. And all shapes are represented by same number of corresponding landmarks. Say for example, here you can see that I am taking 14 points of interest to represent the diagram, right? Similarly, in every object delineated structure, I am having the same number of 14 points. So with the 14 number points for each shapes, I drawn different, or the experts drawn different representations. These all are dependent upon different experts. Okay. So first the shapes are aligned to eliminate irrelevant differences in pose between different subjects. Here a kind of registration is they are doing. So all the shapes are aligned to eliminate irrelevant difference in pose between different subjects. After that, they are doing a principal component analysis on the landmark coordinates to yield the mean shape of the main modes of variation around the mean. So they will find out the mean of all, and they will find out a variation from the mean to left or right. Okay, so then this shape model can be used for automated segmentation of the lung in a new images by augmenting it with photometric model of the local intensity patterns around each landmark. So once the registration process is over, we can use it as a mask for segmenting other lung lesions. So here the flexible shape fitting makes use of a more or less global parametric model of the image appearance of object, which including the photometric or geometric or contextual properties. That is fitted into the actual image data by optimization of objective function that evaluates the goodness of fit of the model instance. Simply they are taking a curve which is an exact replica, not exact replica of the object. Then they are trying to fit this curve to the object, and then they are using some optimization algorithm to fit the curve properly. So once the fit is ready, you can say that that is the corresponding delineated marking correspond to the particular object. So this is what we call flexible shape fitting. Here, the name shape fitting comes because we are going to take the shape of the object and we are trying to fit there in the object. So that's why it is known as shape fitting. So when we come to the pixel classification, the second methodology, the pixel classification aims at assigning an object level or its probability to each voxel in the image individually, mainly based on local intensity information alone. So the classification can be supervised or unsupervised. Here what they do is, they will split the entire image into small voxels, that is volume pixels. Okay, and each volume pixel is processed locally. So here this picture shows a pixel classification mechanism where example of a CNN trained on organ risk delineation in a head and neck CT scan used for treatment planning in radiotherapy. So here, the neural network predicts the object levels in a small patch around each voxel based on local intensity information at different scales, and it is trained by comparing its pre-detection, that is yellow, to the manual ground truth run. So you can see here, this is a CT image, this is a corresponding ground truth I am providing. So this will be taken by the network and it will segment the portions. And here you can see that the yellow lines represents the predicted value, and red lines here inside you can see that there is a red line. These predictions are much more accurate, that's why both lines are blended together. So the red lines here represents the ground truth and the yellow line represents the predicted one. Okay, so the classifier generates delineations of multiple organs simultaneously. So here you can see that here you are giving the original image with the ground truth of different portions, right? So all the different portions are detected in the same algorithm. So we can detect multiple lesions in a single algorithm. That is also possible if you have labels or ground truth for the corresponding images. So this is based on pixel-based classification. Here we are considering each pixel by pixel. For example, this portion will be one voxel, this will be another voxel, this will be another voxel, like this you can consider. So we are splitting the entire image into different voxels. Each voxel is operated. So this is all the operations are based on pixel level. Previously we have done with the shape. Now we are doing with the pixel. So this is what we call pixel classification methodology in model-based system. So here also some fundamentals issues may be there. The first one is the explicit versus implicit representation of geometry. So in this, the object shape can be described using points, contours, or measures with the explicitly specified coordinates, or as a picture with implicit geometry implied by the image grid. So this flexible model to image fitting using an explicit geometric model representation is typically driven by local photometric features along or inside the object boundaries while fitting an implicit iconic model. So in this implicit model, we are doing with the contours, and on the other hand with the explicit we are going with the pixel. And second is the global versus local representation of the appearance. So in this case, we can consider the image as a whole. So that time we are getting global features from the data. But when we split the entire image into small patches, that will give more local information. It may be much better compared to global. So that is the difference between the global and local representation. And next is deterministic versus statistical models. Shape models in medical image analysis are often deterministic. So that is, they are mainly heuristic. For instance, an object represented in a 2D flexible curve with intrinsic smoothness properties, a 3D elastic mesh or deformable template with physically based deformation properties. The objective function used for fitting the model to an image is usually formulated as an energy function or similarity measure, which typically consists of weighted combination of an external energy term assessing the agreement of fitted model instance with relevant photometric features derived from the image data, or one or more internal energy terms or penalty functions. So you can either represent it in the form of an external energy, that is the shape factors, or we can go with the internal energy. So these are the two And finally, the data congruency versus model fidelity. So our objective function to be optimized during model fitting typically shows a trade-off between assuring the fidelity of the model instance to the expected object properties. That means how the model is fitting to the data at that instant. So with the deterministic model approaches, this trade-off becomes apparent in the form of weight parameters that have to be set heuristically to balance the influence of different terms of objective functions to obtain suitable behavior of the model in a specific application. So these are the fundamental issues we are facing in these model-based systems. Now we are going to a deeper understanding of deep learning. So in computer-aided diagnosis, there are a lot of classical approaches. The classical way to do a pattern recognition for computer-aided design is done by designing handcrafted detectors, that is using machine learning. And these handcrafted detectors are constructed with the bank of special filters called kernels or templates. And these performing convolution obtained by performing convolution by shifting a small filter over the entire image, raw by raw respectively, then giving rise to high dimensional feature space, you are getting a high dimensional feature data. And clusters, this feature space are separated by so-called classifiers in the desired classes. So this is the classical algorithm we are using. But when we comes to a pictorial representation, we can see that the classical approach having a test set, training set. First we will take the data, we will do the pre-processing. After that, for getting the details, we are going for segmentation. After segmentation, either you can go for feature extraction like Gabber, Temura, local binary patterns, Sandvik moments, and other regional properties, and you can have more number of features here, right? So that will be given to the feature selection through entropy. So feature selection will give you the features which are relevant for the information making and making decision making. So that will be given to the stored feature. You can store it, you store it in the system and you can use it later. Then you have to take the ground truth and classify with your classifier. Or in other words, after segmentation directly you can extract features, selected features, and you can go for classification as normal or non-normal. So this is the entire classical approach. So when we come to the neural networks, so that as you know, this figure represents a human neuron. So where here we have different inputs x1, x2, x3.
ఈరోజు రానని మెయిల్ చేసింది సార్ తనకి రేపు ప్రీ ఎగ్జామ్ ఉందంట సార్
Hello.
ఫార్వర్డ్ చేశారు ఎలా బ్యాగ్ కట్ చెప్పండి అంటే
Hello. Somebody
looks like some
Participant.
please mute the mics.
mic. I request all participants to put off your mic, please.
So here we have x1, x2, x3, etc. xn inputs are there. So the associated weight are w1, w2, etc. wn. So here we have getting a sum that is nothing but the product of the input with the associated weight. And after that we are going for an activation function and nonlinear activation function. So after that we are getting the output. So this is actually an exact replica of the human neuron. So it is now we call it as an artificial neural network or ANN. So here actually we have a network like this, but in actual practice we are having y is equal to sigma of w0 plus summation wi xi. So where this w represents the bias, so bias will allow the nonlinear function to shift based on the nonlinearity. So this is the neuron which is called as artificial neural network or ANN. So this is the basic building block of the neural network. And when we come to the deep neural network, so we have more than one or more hidden layers, then we can call it as a deep neural network. So here we have an input layer and there are a few more hidden layers and we have an output layer. The basic design idea behind this neural network is that the number of hidden layers should be greater than the number of input layers. So that is the first condition. So when you give a general image for learning to this neural network. So in the first hidden layer, it will extract the edges of the object. And in the second hidden layer, it will extract the combination of edges. That means shapes, some shapes it will get. And at the hidden layer 3, finally get some objective models. These objective models are nothing but abstract representation of the original image which we have given. So this is how the learning happens in a neural network. Then the entire network has to be trained. So the training process taken place by means of forward-backward propagation. So in this forward-backward propagation, so when you give an input image, so it will learn through the hidden layers, and it will reach at the output layer. So here I am giving this image as a lady's image, and I am giving a corresponding label for this. So whenever this data reaches at the output layer, it is checking with the original image, and if it is not exactly same, it will return a value called loss. So this loss is fed back through the network from back to front side. So this is known as back propagation. So in forward path, we are passing this information through the network, and you are getting a loss over here between the difference of actual one and predicted one. So this loss will be propagated back through the network to adjust the weight. So here loss is nothing but the L. So here we need to find out the gradient of the loss, that is dou L by dou W, so in terms of the weight. So we are taking the derivative of this loss. So this will give you, X or Y, dou L by dou X or dou L by dou Y. Since it is a two-dimensional image, you have to take the gradient along X direction and Y direction. So you have to take dou L by dou X and dou L by dou Y. So this will give you the gradient. So this gradient has to be reduced from the initial weights. So initial weights are, we have seen W1, W2, W3, etc. right? So our new weight will be W11, which is equal to W1 minus eta into dou L by dou X. So where this is the gradient and this is the learning rate. So likewise, we will modify our weight. Then we again move forward. Again, the loss will be there. Again, come back. This process repeat until our loss become minimum. So this is how the network trains. So one of the example for a convolutional neural network for classification is the AlexNet. It is developed by Alex Krizhevsky in 2012, and it is won the ILSRVC challenge prize, first prize. And this is actually a classification network which is taking an image size of 224 by 224 by 3, and it is having a set of convolutional layer followed by max pooling, and two set of fully connected networks. One is having 2048 nodes and another having 1000 nodes. So this is a very lightweight network. So the next is why we going for this convolutional neural network or deep learning when compared to the recent years, because the one answer is big data. So the primary key for successful deep learning applications such as image classification or self-driving cars, face recognition, etc., the availability of big data. So when you see the ImageNet database, it is having thousands of images with 1000 category, more than 1000 category. So a lot of images are available for training. So that led us to work in deep learning. And you know that Google, Facebook, Amazon, and Microsoft, Uber, Baidu, Apple, Tencent, etc. are using this kind of deep learning applications. They offer many services for free, such as Google Translate, Google Photos, Facebook face tagging, and Google Street View. And second is the development of graphical processing units. I think you know that to implement these deep learning algorithms, we need higher-end GPUs to process this large set of data, right? So the graphic processing unit is a single additional computing chip located on the game card in the PC or laptop with typically hundreds of parallel processors. So it will do a parallel processing. And one of the giant GPU company is NVIDIA, and they are typically programming in the language known as CUDA. So when you have a GPU system, you have to install the CUDA version for the particular package and you have to use it. So due to the development of graphical processing unit and parallel computing system, we are now using deep learning more compared to the recent days. So another point is the development of smart network architectures. A multitude of deep neural network architectures have been developed for specific purposes. That is convolutional neural network for images, residual neural network for faster training, recurrent neural networks for temporal or sequential data, that is for video data, units for biological image segmentation, generative adversarial network to generate images from learned specific styles. So if you have a less number of images for your training, as I told earlier, we can go for image augmentation by simply flipping, shearing, or rotating the image. But better than that, we can go with the generative adversarial network. So these will create synthetic data. We will see the GANs in the next few slides. So it can generate synthetic data, so that will help us to multiply our small image data into large one. So the pointers on the web are grand challenge. So some of the methodology, common platforms are available for this medical image analysis. So one of the website is a Grand Challenge. So in Grand Challenge, you can see that they are providing a lot of standard data sets. So it's a challenge where you can find a lot of data. You can register for that particular challenge and you can access their ethically clear data, and then you can use it for your work, and you have to participate in the program and you can upload the result in the program, and you may get sometimes the prizes. So all challenges have prizes. So they will give annotated data. That is advantage. You don't need to go to contact a doctor for annotating your data. So it is much better option. Second thing, tutorial papers. You can refer tutorial papers on this medical image analysis. Then NVIDIA.com, there is a blog. So in that blog, they are giving details regarding what are the trends in their GPU. So what are the packages that can be associated with the GPU. All these informations are available. And next is Medium.com. It is another blog. You can see the contents over there. It's the scientific writing is more and more accompanied by blogs. Written magazine is there. Styles exploiting interactive multimedia is available in the Medium.com. And the next one is arXiv.org. So it is a scientific publishing. Generally, you know that it is too slow for modern computer science or any research area. So this arXiv contains the recent literatures before publication. So you will get to know what are the current trends by looking at the arXiv papers. So this will give you a more idea what is currently going on. So you can refer to arXiv. Then ConNet.js. It's Karpathy interactive demos of deep learning teaching examples running on any browser with visualizations of what the layers do. Each convolution layer, what the operation done by the convolution layer, that we can visualize in the ConNet.js. And finally, one more thing is there. It is Keras.io. Keras.io will give you the programming codes in Python in a Keras backend for all the medical image processing or general image processing applications. Keras.io. You can check and find out more coding. So you can try their own codes. They will give sample codes. You can try and you can learn how to do the process. So now the thing is how to develop a artificial intelligence application. So as we know that AI being pointed as the main driver for fourth industrial revolution 4.0. So AI have introduced in daily life applications speech and face recognition, self-driving cars, and natural language processing. So AI was the growing success of specific type of ANN called convolutional neural network. That's what nowadays we are using. And hidden layers of this architecture are formed by convolution layers that apply a filter or convolution to the input data. So what is the difference between ANN and CNN is that in a CNN, we are replacing all the hidden layers with the help of convolution. So that is the difference. So the convolution allows for significant reduction of number of free parameters of the network and does not require the previous extraction of handcrafted feature. So when we apply this convolution on the images, it will directly give the features. So no need to find the feature by our own. So it is an end-to-end learning. So it is easy for us to operate with deep learning. So now we can see some applications of AI and radiology. So first one is the acquisition. So in image acquisition, the first point is the creation of study protocols. So the creation of study protocols means the protocols for taking the image of a particular specimen and then optimize the MR and CT image quality. So as you know, when you take the images from MRI or CT, due to the human perturbations in human body, or maybe due to the movement of human, there may be chance of data may be having artifacts. So that need to be optimized for getting a better quality. Then assessment of quality. After getting an image, we need to assess whether the image is having good quality or not. So that also there. Next is the image interpretation. So automated hanging protocols, then radiomics and imaging biomarker analysis, then automated image interpretation. So all these comes under this image interpretation. The reporting, speech recognition. So when the radiologist is scanning the object and he is topping the results, the speech recognition system has to identify it and convert it into text, that is text translation. Then automated annotation through keywords. If he is telling some keywords, automatically it should annotate. Then knowledge extraction through data exploitation. So process radiology reports, image-based search engines. Say for example, I am giving a part of the image into the search engine, it should give the proper image. Then population health, management of all data. These are some applications of AI in radiology. And the first one we will see the development of AI applications in radiology. First is the clinical problem definition. Second one is engineering the AI technology. Third one is the data collection. Fourth one is the data annotation, training and testing. So first we will see the clinical problem definition. So the golden rule for development of successful and technological solution is to clearly detect clinical need and allocate time to achieve requirement definition as detailed as specific as possible. So the radiologist immediate need is not an algorithm performing extra diagnosis. Okay. So they require method to rule out abnormal studies and prioritize them in the work list, minimizing the number of unreported exams, which is a worldwide issue. So this is the clinical problem definition. And when we come to the engineering, the AI technology, once the clinical need is clear enough, the AI technological solution must be engineered. So in this step, we have to choose between creating classifier and regressor. So the output of the classifier will be a group of categories, if it is normal versus abnormal in a structure, right? And the output of a regressor will consist of a continuous value. It may be a kind of prediction. And the classifier or regressor techniques to be evaluated among the available model in ML will be specified. So we have to specify which method we have to go for. Dataset collection. So dataset of imaging studies should be collected. It is essential to preserve the data format across all files to the files of the dataset and to have consistency through the different image files. So next is data annotation. It is one of the most relevant part of the whole image ML development process. Different strategies have been proposed to overcome the annotation deficit. So the creation of more AI-friendly PAC environments. PAC means picture archiving and communication system. So in PAC format, we are making our images. So which would allow radiologists to seamlessly label the case. And it can be achieved by integration of structured reporting validity routines, where the cases will be automatically linked to a set of predefined fields in the database containing findings. So in other words, we can say that the PAC information should contain all the details in an annotated form. So it will be helpful for the people those who are using the dataset. So this is the data annotation strategies to overcome the lack of data annotation in radiology. Solving the lack of annotated data, seamless labeling, hiring expert for case annotation, data augmentation, transfer learning, retrained networks, use of retrained networks, geometry transformations, noise addition, strong supervision, pre-computed editable segmentations, and structured reporting. So when we comes to the training part, typically if you have 100 set of data, so 100% data, you have to take 80% of data for training, okay, the AI models, and 10% is used for validation, and 10% is used for testing. So once the training is finished, using CNN, these weight and parameters are fixed and will remain unmodified along the next step of AI weighting. So when you use a convolutional neural network training, you are taking this 80% data, you are training, Then you are validating with the 10% data and you are getting a good accuracy, validation accuracy. Then your system converges and you are saving the model, right? So after saving the model, we can use the model for testing. So for optimizing this training process, we are using gradient descent algorithm. So gradient descent is a optimization algorithm for finding the gradient of the loss function and minusing it from the weight to process the backpropagation. And gradient descent is much slowly converging process. So in order to increase the speed of the gradient descent, we are going for stochastic gradient descent. In stochastic gradient descent, we split the entire data into small batches. I think you heard about batch size in convolutional neural networks. So that is what here we use batch sizes. So if you split the entire data into small batches, then find the gradient descent, the computation become more easy. This is similar to a complex problem. We will split into small simple problems, right? When we are processing. The same idea here. The entire data set will be divided into small pieces. Then we apply stochastic gradient descent to solve the computational complexity problem. So during testing, we have used unseen images used to evaluate the robustness and generalization of the final model. Fast and requires less computing power because once you train the process network, the training is over. Training will take more time. For testing, it will take a few seconds. So this is a very speed operation. So once the model is ready, we can test it very fast. So for classification problems, we are going to use area under the curve AUC. It is a curve between the true positive and false positive, right? So this is AUC we are using, and for segmentation task, we are going to use dice coefficient or overlapping ratio. That means you have a segmented mask like this, and you have segmented your output like this. You have to compare these two, the overlap between these two. If it is perfectly matching, the dice score will be 1. And if there is a difference, the dice score will be less than 1. Next is the results framework. So results framework is first is the expertise. That means the availability of data scientists is required. Then computing resources, hardware, that is high-end GPUs are required. Then software resources, the packages like Python or TensorFlow with the Keras package should be required. Then data resources, labeled or annotated data is required. So this is the resource framework for medical image analysis and computing. So now we will see some imaging biomarkers and imaging biobanks. So this provides additional value and support to radiologists in the process of diagnosis and assessment. It is a consensus-based multidisciplinary approach and requires regular assessment of the accuracy of quantitative evaluation of medical images and radiomic features, and regular updates of the standardization requirements. Massive amount of radiomic data has to be stored and imaging in biobanks. So the challenges for adoption of quantitative image analysis method within a clinical routine is objective and reproducible, efficacy in the evaluation of disease and treatment, cost-effective, and providing surrogate results for close to the clinical endpoints. So you have a set of clinical findings, right? So whatever the values we have obtained from the images, that should match with the clinical results. So then only we can correlate and say that this is the correct disease. So these are the challenges we are facing in the clinical process. And in a stepwise development, we can see first the proof of concept mechanism. We have to, in a medical imaging system, we have to define first the proof of concept system. The first one is image acquisition. So during different modalities we can acquire. So signal and contrast, noise, spatial resolution, temporal resolution, artifacts, reproducibility, all these things comes out of this image acquisition. Then data processing, we are processing the data. Then signal analysis and data modeling of feature extraction, we are extracting the feature. Finally, measurement and visualization of findings. Then we are giving it to the proof of principle. There we are qualification and validation is done. Then finding the innovative effectiveness. Then we are creating a structured report. So this report should match with the clinical findings. Then we can make a decision. So here, this is the diagram showing the development of biomarkers. So for example, what do you mean by biomarker is the lesion which is responsible for making a decision. Say for example, a nodule in case of a lung cancer. So nodule means that nodule or polyp means a cancerous cell. So that is the biomarker. So if you are able to detect that biomarker in your medical image analysis, that will be correlated along with the findings of clinical data, then we will make a decision. So this is the stepwise development of imaging biomarkers. So then validation. So the imaging biomarkers ideally should be calculated by testing the following variable condition with the same subjects. So we cannot simply find the biomarker. So we have to calculate by testing the following variable condition with the same subject. We have to use the same subject with the different imaging center, different equipment, different vendor, different acquisition parameter, different patient preparation. So based on this, we have to find. For the evaluation of influence of methodology in the obtained measurements, imaging biomarkers should be calculated with the same object and acquisition protocols while changing the following condition. That is operator. That is intra-operator variability, processing algorithm. So when we talk about this intra-operator variability, it is very important. So inter-operator variability means, say for example, I am having 3 experts, E1, E2, E3. Okay. So I am having 100 normal data and 100 abnormal data. Okay. So the first expert is giving 90 data belonging to normal. This is normal, this is abnormal. Normal, abnormal. So 90 data and 90 data. Second expert is giving 85, 90. Third one is giving 91, 90. So in this interoperable variability, so we have to see the 3 expert marking. Okay, these 3 expert marking, and we have to take the intersection of all the findings. That means here this fellow given 90 normal, 85 normal, and 91, but 3 of them classified as 85, right? So 3 of them given, one is given 90, another one is given 91, third fellow is given, second fellow given 85. So we have to take a combination of all. That means 85 to be your result. Similarly for 90, 3 of them given 90, so you can take 90. So the minimal should be taken here because 3 of them analyzed. One fellow have doubt that 5 is not belonging to the normal category. So we have to choose like this for intra. But interoperability means expert 1 will be used, but at 2 different times. This is first week. This is third week. In a month, give the data set to the expert in first week. Then he is experting, using his expertise, he are giving 90-90. Second time, after 3 weeks, you are giving. In the third week, 2 weeks here, we are giving. He is giving 85-90. Then you have to take 85. Okay. So this is the variability in intra-oper. This is in inter-oper. So operator. So this is the problem. So we have to consider more number of expertises to mark or annotate the same data. Then only we will select the final result. Otherwise, with a single expert annotation, it is very it's not good because we are only considering with one expert. We need to consider both the intra-oper variability and inter-oper variability in this case. Next is the processing algorithm. So you can use different algorithms for the same object and same acquisition protocols, and you can verify whether it is giving some good results or not. A different algorithm is one can use VGG network, another one can use AlexNet or something like that. So then imaging biobanks. So imaging biobanks means it's an organized database of medical images and associated imaging biomarkers shared among multiple researchers linked to other bio repositories. So it's a combination of all the data from different researchers. So predictive biomarker, that is used as a tool to predict progression and recurrence of disease. Diagnostic biomarker, used as a diagnostic tool for identification of patient with the disease. Morphological biomarker measuring the size and shape of the macroscopic structure in the body. Staging biomarker, used as a tool for classification of the extent of disease, in which stage you are. Monitoring biomarker, used as a tool for monitoring disease progression and its response to treatment. So these are different biomarkers in imaging biobanks. So in imaging biobank, we have 2 sections, population-based and disease-oriented biobanks. In population-based biobanks, it is a developed collection of data from general population. It aims to identify risk factors in development of disease, to develop prediction models for stratification of individual risk, and to identify markers for early detection of the disease. This is for population based. But on the disease orientation biobanks, they develop to collect multiomics data from oncologic patients or patients affected by neurodegenerative disease in order to generate digital models of patients. So here we predict the risk of prognosis of cancer or degenerative disease. It's already been cancer. We will detect the prognosis of cancer from different stages. So imaging biomarkers and biobanks in AI. So imaging biomarkers are an essential component of imaging biobanks. So determines both precision and accuracy of measurement as well as their margin of confidence. And the imaging biomarkers generated by AI can be evaluated either in a short-term or long-term measurement tool. So we can use AI for generating imaging biomarkers. And imaging biomarkers do not only consist of images, but other data, that is biomarkers that can be extracted from them through computational analysis. So biobanks is nothing but collection of data along with different imaging biomarkers. So applications of AI beyond interpretation. So this is the application of AI beyond interpretation. So first one is patient referring provider. From that we have imaging appropriateness and utilization. Then patient scheduling, imaging protocol, imaging modality of operations, quality evaluation and improvement and dose reduction, hanging protocols, work list optimization, staffing optimization, interpretation and reporting, communication follow-up and billing, referring back to the patient. So this is the applications of AI in a patient-based system. So these are the detailed information, imaging appropriateness and utilization, and patient scheduling. Patient scheduling means optimization of scheduling can be enhance the patient experience and has positively impact on patient satisfaction. So we can schedule them depending upon the availability of the radiologist, the doctor, all those things. Second, imaging protocols. So imaging protocols means your electronic medical record, recent office visit notes, prior hospital admissions, discharge summaries, past surgical history, medication list, allergies, relevant lab values and pathology results. These are the imaging protocols they have to consider. So we can digitize it through a kind of technologies. Then improve image quality improvement and acquisition reduction in MRI. So we know that for taking an MRI image of a whole body, it will take 70 minutes. If you develop AI-based MRI reconstruction technique, you can take image in 5 or 10 minutes. So that will improve the acquisition time and also the quality. Then quality improvement means you know that when you take a CT image from a CT machine, there is only low dose information is passed through your body because high dose information may ionize your tissues and that may lead to cancer. So you can give a low dose CT and you can take the CT image with a low resolution and you can use image super resolution using deep learning methodologies to improve the quality of the image. So that way also we can use deep learning or AI in image quality. And image transformation. Transformation means image transformation AI can be used to simulate images that are of different sequence. Say for example, creating pseudo CT image from MRI. From MRI image you can create CT. So fully connected, fully convolutional neural network with conditional generative adversarial GAN can used for generating PET from CT. So if you have CT imaging scan in your system in your lab, you are not having PET because PET is radioactive and it is high cost. So if you are wanted to generate a PET image from CT, you can use deep learning methodologies. Here we will show an example. So here this is known as virtual PT from CT to PT. So here this is a CT image and here we are using a trained fully convolutional neural network followed by a trained conditional GAN. So using this conditional GAN, we are generating a PET-like image. So this is the original CT image and this is the PET-like structure obtained from a CT. So here this FCN giving good enhancement of tumor and bad active surroundings. The conditional GAN give good refinement in the FCN output. Bad enhancement of tumor are standalone. So when you club these together, you will get a better representation of the image. So you can generate pseudo images of PET from CT. So this is also possible with deep learning. So then the image quality evaluation. So by visual inspection, you can go for quality evaluation. Then hanging protocols. This is hanging protocols are also known as the default display protocols. And these protocols are image order, orientation, modality, anatomy, that is body part, image plane, window level, pulse sequence. For example, in MRI, which sequence, T1, T2, DWT, what sequence is used. These are the protocols you have to take into account. So next is reporting. So AI in reporting and documentation can improve differentials and diagnosis. So machine learned models demonstrate high sensitivity, slight loss of specificity, overall higher area under the curve, that is AUC values. And best accuracy was achieved when both the natural language processing and machine learning based algorithms were optimized concurrently. So the text summarization, report translation. So here also we can use AI. So as you know, the NLP and deep learning can be used to generate radiology reports that are tailored to different number of overall patients there. And it helps patients to become more engaged in their own healthcare through healthcare literacy. So input could include patient age, native language, education level. But here the constraints are greater adaptability may be achieved if the patient interacts with the machine and actively look up definitions while reading their report. So next is speech recognition. So whenever the radiologist is finding the anomalies in the image, he is talking about this and the speech recognition system should identify. Then after that, the speech recognition system should convert it into text format and generate a report. So in this area also we can use AI. So next is the follow-up. So follow-up care for patient becoming increasingly important in healthcare transition. So AI can be used to develop system to extract follow-up information from radiology reports. So used to track and monitor patient follow-ups. So we can use AI for this in identifying patients where he is following or not following. So we can detect that by using AI technologies. Then work list optimization. Sorting of cases in order of urgency. So see, when you are going to a hospital, depending upon the urgency, if the cases are arranged or sorted, it will be easy. So the doctor can give more weightage to the most needy one. So this kind of algorithms can be developed by means of AIs, and this will help work list optimization. Then staffing optimization. So scheduling of the staff, time of day, day of the week, coverage location, all these factors have to be considered, and based on that you can schedule your staff very effectively using scheduling algorithms. The challenge is using vacation and meeting time. That is a problem. If sudden meeting or some leaves that happens, it is difficult. Otherwise, it is fine. Solution is AI has potential to optimize staffing for radiology as in other industries. So we can solve this, but there will be some issues still. Then business intelligence and business analytics. So we are using high fixed cost due to price of imaging equipment, personal and advanced knowledge acquired for delivering high quality imaging diagnosis and treatment. So we need to identify and quantify metrics such as diagnostic accuracy, turnaround time, imaging modality utilization, wait times, among others. So business intelligence tools have been used in financial industry for years and can be transitioned successfully to the healthcare environment for the process, quality, safety, and financial performance improvement. And both BA and BA tools augmented by AI have the potential to add value to entire imaging value chain. So we can define the workflow, efficiency can be increased, we can provide a better service, cost effectiveness, revenue generation, then quality and safety, and the patient outcome and satisfaction. Next is the content-based image retrieval. If you have a small image information, based on that content, you can retrieve the whole image. For example, you are going to a hospital, your medical data is there. For example, you take a small portion of your disease details and you give it into the system. Suddenly, it will retrieve all your information. So this kind of activities can be done using AI. Then patient safety. The prime important thing is the patient safety in healthcare. So machine learning can help on patient safety is boundless. AI is neither astute or intuitive, and physicians will essentially to design, enforce, and validate and revisit AI products to ensure patient safety while improving healthcare services. So you can say that AI can be used for these purposes. At the same time, we have to make sure that the AI system is not making a wrong decision. If it is wrong, it will affect the patient. So mainly we have to consider the patient safety when we go for these kind of activities. Then for billing operations also we can use natural language processing or machine learning based system. Then patient experience. So we can get a better experience with this AI in terms of diagnosis, treatment, prevention practices, improving patient health education and overall patient experience. So this is one example, AI in computer-assisted evaluation of chest pathology. So I will finish it within 5 minutes. So here, just we are finding some lung nodules in a lung. So here you can see that this is an X-ray. So this X-ray is giving some details, but due to the presence of the bone structure, you are unable to get a better, clear idea of the nodule. This is the nodule over here. So when you take that portion into zoomed version, here you can see that this is a nodule. So this nodule is actually unable to see through the X-ray. So that's why we are going for CT kind of scanning. So in CT, we can see that the nodules are clearly visible here. Okay. So the nodules can be clearly identified. So we are moving to CT. So when we come with the CT, so it will give more detailed idea regarding the presence of polyps compared to X-ray. So here also we use a lot of CT, and you can take a low resolution image and we can increase the resolution into high resolution by means of deep learning methodologies. So in computer tomography, the main problem is it requires much greater number of images to be evaluated. So for that, we develop an algorithm to detect polyp in CT and apply that algorithm, and it will detect polyps in particular slices of image. Then after detecting, the radiologist can check and verify. So that is, a computer-aided system can help the radiologist. Generally take the CT scan, put it into the algorithm. It will give you in which slices the polyps are present or nodules are present. Then the radiologist can look into that and he can find this. So this is one of the CAD system which is helping the radiologist. So here you can see that using a software, AI software, the nodules are found out. Here, nodules are found out. So after finding out by the algorithm, the radiologist can verify this. So here this in a lung cancer radiomics. Radiomics means processing of radiological imaging data. So here first we take the data acquisition, region of intersection, region of interest ROI segmentation, then feature extraction, then taking the data, details, and classifying. Second thing, multispectral imaging. You can take either CT or PET. You can fuse this together. This is PET, this is CT. You can fuse it together so that you are getting a better structure of the nodule or tumor, so that can be detected. Then you can either go for genomics or pathology or clinical references. Based on that, the radiologist can find out whether this fellow is having a malignant or benign nodule. So future directions are generative adversarial networks. So as you know, GANs are used to generate synthetic data. So here we have the original data. There is a fake data which is generated from a noise, and that will be discriminated in a discriminator, and then the loss will be taken or the difference, and the difference will be fed back to the system. And this process repeat until whenever this original image is equal to the fake image. So this is the basic idea behind GAN, and these are the GANs we are using for different applications or data augmentation, photos, emojis, face aging. I think you are using some apps in Facebook, face aging. That is done by means of GANs, photo blending, super resolution, all those things. So here you can see some popular GANs. Style GAN, it is generating realistic faces from this. This is the input, and from this it is creating some realistic faces. Then cycle GAN. Cycle GAN is used to generate one image from another. So here it's a horse image, you are getting a zebra image here. So horse to zebra, similarly from zebra to horse. We can generate more data. And this is BigGAN. This is for generating high quality images with super resolution. These are super resolution images using BigGAN. And pitch to pitch, paired image to image translation is there. So there we can use labels to street scene, input to aerial to input map, labels to facade, day to night, input to grayscale, black and white to color, edges to photo. We can convert using popular GANs like pitch to pitch, paired image to image translation. And cycle GANs are there. So cycle GANs are there to generate data for data augmentation. So this is actually a true contrast CT. Contrast CT means we are taking the CT scan along with injecting a contrast agent through the body. So when the contrast agent is passing through the particular portion of the body, we will take the scan so that we will get a better perception of the image. So here this is a true contrast CT and this is a synthetic non-contrast CT generated by CycleGAN. So these are the CycleGAN images. You can see it is more closer. So this is a normal chest X-ray and this is a COVID X-ray. This is generated in our lab by our students and this is actually a normal CT. Using this normal normal X-ray, we have generated a COVID X-ray. So here you can see that the COVID lesions. So if you have less number of data for training purpose, you can use CycleGAN for generating more and more data. So with this, I finish my session. Open to questions. Thank you.
Dr. Varun, thank you so much for your excellent presentation. Now I would like to invite questions from audience if there's any. Audience can unmute and ask questions.
Dr. Varun, can you hear me?
Yes, sir.
So I am Vijay. I have a doubt on just I want to discuss with you regarding the data annotation. Maybe data annotation or data labeling before pre-processing. Usually all the publicly available database are automatically labeled or annotated. But if we acquire our own data or signal, so the data labeling part research stuff is very low. So how about the machine learning and deep learning role in data labeling and annotation?
So data labeling is here also we need an expertise for this process. You can use it using annotation tools are available. So there are certain deep learning or machine learning annotation tools are available. You can use it by your own, but that is for the sake of just trying the algorithm. But when you deal with a medical image, definitely you have to get a consultation with the radiologist or the doctor.
Yes, yes. Okay.
Because they only know exactly what is happening in the image. So you can use the annotation tools, but still you have to show it to the doctor and you have to get verified.
Okay, so the validation part should be done along with doctors.
Yes, definitely.
Okay, fine.
Even for the checking the significance of the standard data set, we have used a poly image classification in the colonoscopy. So there we have a standard data set, but still we given to two doctors and they have verified. Finally, when we verified, it was correct only. So it will give more advantage.
Okay.
If you test with a physician or a doctor or a radiologist, it will be good.
Okay. So apart from our proposed algorithm or the method, is there any existing tools available for data labeling?
Yeah, some tools are available. I will just give the names in the chat box now.
Okay, fine. Thank you.
Thank you, Dr. Vijay. Can we have more questions from other participants too? Hello?
Yes.
Sir, is there a performance metrics available for the segmentation process?
Yes, performance we are finding by means of IOU, that is intersection of our union, IOU, or DICE score.
Okay, sir.
So IOU means intersection of our union means you, I think I shown one figure. So we have a mask, right? So mask will be there, annotated mask will be there given by the doctor. That mask to be compared with the detected or predicted value. If there is a perfect match, IOU, that is intersection of your union will be 1. That means your algorithm is perfectly segmenting the data. If it is less than that, it is not that much. If it is 0 means there is no matching.
Okay, sir. Sir, if we have our own data acquired using any modality like microscopy or something, in that case, we don't have the ground truth or the mask available. In that case, how this type of performance metrics will be useful, sir? Or is there any other metrics that can be used?
For what kind of application? Segmentation or classification?
Segmentation, same segmentation, sir.
Segmentation, these are the values. Actually, you need ground truth.
Okay.
You cannot simply, then otherwise, how you decide your algorithm is segmented properly?
Yeah, that's a confusion we had. That's why I want to get it
So
clarified.
you need definitely a ground truth for this process.
Okay, sir. Thank you, sir.
Thank you, Dr. Varun, for your presence in our FTP. It's today, 3-day FTP, and this is the second day. Thank you for your excellent presentation, as well as your immediate acceptance to join for this FTP. Thank you, Dr. Varun. Thank you so much. We look forward to your continued support to us whenever we invite you, sir. Thank you so much.
I also would like to thank SSN for inviting me for this FTP. So I given 3 names of annotation tools in the chat box, so you can check that one. So thank you for the program, and thanks to all the participants for their kind patience. Thank you. Have a nice day.
Thank you, sir. Thank you.
Thank you.